This video is all about another type of energy, potential energy, otherwise known as the energy stored in an object due to its position within a system. There are two types of potential energy that we'll learn about in this video. The first type is called gravitational potential energy. And the second type is called elastic potential energy. Gravitational potential energy is the stored energy, or potential energy, that is associated with an object's position relative to a reference point. A reference point is actually more of a level where we assume the gravitational potential energy to be zero. So at this point, gravitational potential energy is zero. You'll notice that symbol U sub G is the symbol that we use for gravitational potential energy. Gravitational potential energy depends on three things. It depends on the mass of the object. Because it's called gravitational potential energy, you could probably assume that it depends somehow on gravity, or the gravitational acceleration. And then also the height. The height in this case is the distance above or below the reference point. You'll notice nothing here has a vector. Everything is a scalar. And that means that when we're plugging in G, we plug in a positive 9.8 meters per second squared. However, gravitational potential energy can be negative. If your object is below the reference point, sometimes called the reference level, then you should use a negative value for H, yielding a negative value for the gravitational potential energy. Let's look at an example so you can understand a bit more about what that means. In this example, we have a block that is traveling around what kind of looks like a roller coaster course. We're given three different heights for three different sections of this course, and we're asked to find how much gravitational potential energy our block has at each of the heights with two different instances. The first one, the reference level, again that's another name for the reference point, is at the ground. So in part A, this will be our reference point, or reference level. And then in B, we're going to talk about it being at height 1, but we'll deal with that later. So in each case, we'll be using the equation gravitational potential energy is equal to mgh. And like you could probably guess, our mass in this equation has to be in kilograms. Our value for G has to be in meters per second squared. And our height has to be in meters. That all works out so that our gravitational potential energy is measured in joules, just like any type of energy that we ever use for physics. And so we'll start off calculating how much energy it has at H1. So we know the mass in each case is 45 grams, but we have to convert that. Pause the video and convert that to kilograms for yourself right now. You should have found that the mass is equal to 0.045 kilograms. We know G is a positive 9.8 meters per second squared. Again, we use the positive due to the lack of a vector symbol above the G in the equation. And in this case, height, H1, it tells us is 15 centimeters above the bottom, which is where our reference level is located. Again, we have to convert that to meters, so I get 0.15 meters. When I plug all that into my calculator, I get a fairly small amount of energy. 0.066 joules. That's okay, because this is a pretty small object. Let's try the same thing for H2. Now the nice thing for each of these problems is it's the exact same mass, the exact same value for G, just multiplied by a different number. In this case, we have 0.30 meters instead of 0.15. Because the height is twice as big, my energy is twice as large. 0.13 joules this time. Go ahead and calculate the value for H3 on your own right now. You should have found that it's equal to 0.035 joules. Hopefully that wasn't too difficult for you. Now let's look at Part B. Part B changes where the reference level is located. In Part B, my reference level is right there. So when I'm plugging in my heights, I need to pay attention to how far away they are from that reference level. Again, we define the reference level to be the point at which the gravitational potential energy is 0. So at H1, my height is equal to 0 because H1 is the reference level. Therefore, my gravitational potential energy is equal to 0. At H2, we multiply that mass times g. The height at H2 is going to be the difference between H2 and H1, which is 15 centimeters or 0.15 meters. In this case, I'll end up getting a value of 0.066 joules. And then for H3 is located below my reference level. That means that we use it as a negative height, and in this case it would be negative 0.07 meters. This ends up giving me a value for the gravitational potential energy of negative 0.031 joules. Now you might be wondering, why in the heck and what does it really mean for potential energy to be negative? Well, that'll make a bit more sense when we talk later about how we use potential energy. For now, just accept the fact that if you're below your reference level, the potential energy is negative. Earlier in the video, we learned that there were two types of potential energy that we would study. The second type is elastic potential energy, or a potential energy that's associated with the deformation of an object and its tendency to want to return to its undeformed state. Okay, that might be a little bit vague here. Let's talk about some examples. We know that when we stretch a rubber band and let go, it goes flying. That's due to the fact that stretching the rubber band is a deformation, and so you're putting elastic potential energy there. Another example would be when you bounce something on the ground. When a ball bounces on the ground, it deforms slightly. Usually not so much that you can actually see it, but it deforms enough that it stores some elastic potential energy in it. And then that elastic potential energy eventually gets converted to other types. A third example would be the one that we use most commonly, which is a spring. If I take a spring that normally looks like this, and I compress it so that it's really tight together, and then I release it, it usually goes flying upward. That's because it's been deformed, and it has a tendency to return to its undeformed state. Hopefully that helps with identifying when there is elastic potential energy. Now we know that we can also calculate elastic potential energy. Now, each object that has elastic potential energy has a different equation for finding it. So we're only going to deal with one type of elastic potential energy, and that's the elastic potential energy that a spring has from being deformed. So we'll use a u sub s for this equation. That elastic potential energy is equal to 1/2 kx squared. K is something called the spring constant. It tells us about how stretchy a spring is. That's my very unscientific term, how stretchy it is. If you have a small value for K, then it's really easy to stretch the spring. It's very stretchy. If you have a larger value for K, then the spring is very stiff. So if you were to try pulling on the two ends, it would be very difficult to stretch it. Now, small and large values are kind of relative terms. The k can get as small as being a fraction of the whole, so you can get 0.02, 0.0036 for k. And it can also be very, very large, can be in the hundreds or in the thousands. So, saying large or small are kind of relative terms. Another important thing to know about the spring constant are the units. It is measured in newtons per meter. X in this equation is the amount that the spring has been stretched or compressed based on its original length. You'll understand a bit more about that when we look at our first example problem. And of course, just like any other type of energy, elastic potential energy for a spring is measured in joules. Okay, let's take a look at that example. In this example, we're looking at a toy that you may have seen before when you were a little kid. It's one of those toys where you press the top down, it's got a spring in there, and then it eventually pops upward a little bit. That spring in this case has a relaxed length of 2.4 centimeters. And the toy is compressed 1.5 centimeters before being released. In other words, using your hand, push the toy down 1.5 centimeters. It tells us that the spring stores 2.7 millijoules of energy. We're asked to find the spring constant. Okay, it's important to pay attention to some of those units in here as we're doing this. We know that we're dealing with elastic potential energy. So U sub S equals 1/2 kx squared. The thing we're looking for is that spring constant. So I'm going to solve my equation for that variable. And I'll do so by first multiplying both sides by 2. So I get 2 times the elastic potential energy is equal to kx squared. And then I'll divide both sides by x squared. So I get that the spring constant, the thing we're looking for, is equal to 2 times the elastic potential energy divided by the distance of compression squared. So 2, it told me that it's 2.7 millijoules. We have to convert that value, of course. So I end up converting it into 0.0027 joules. And then I divide that by how much it's compressed. Now in this case, we're given 2 different values in the problem. We have to decide which one to use. Well, the definition of that x in that equation is how far the spring is compressed. That doesn't have to do with what its original length was. So the value that we plug in into our denominator here is this 1.5 centimeters, except we have to convert it first. 1.5 centimeters is really equal to 0.015 meters. And of course it's important to square that value. When I plug all of this into my calculator, I end up getting that the spring constant of this spring is equal to 24 newtons per meter. It's kind of a value right in the middle. It's not super, super stretchy, but it's also not really, really stiff. Hopefully now all of these different types of potential energy make some sense to you. We'll learn in class about exactly how we use those potential energies with something called the conservation of energy.